All right, ready to dive deeper into quantum computing. Today, we're going beyond the basics.
Yeah, we're tackling quantum algorithms. This is where things get really interesting.
The quantum algorithms, they harness the strangeness of quantum mechanics to solve problems in ways that, like, regular computers just couldn't.
It's a whole other level of computational power. And today we'll see how these algorithms work, what makes them so unique, and just glimpse their potential, really.
It's mind-boggling. Our mission today is to understand, how they work, what makes them special, and the potential impact. What could they be?
And it all starts with quantum parallelism.
Yeah.
This concept is at the heart of it all.
Okay, parallelism. It's like the idea that a quantum computer can perform multiple calculations, but at the same time.
Exactly. Imagine a coin. A classical computer only sees one side, heads or tails.
Right.
Quantum computer, superposition. It can see both sides simultaneously.
Oh.
Now scale that up to qubits. You have a system exploring so many possibilities all at once.
So instead of tackling problems one step at a time, a quantum computer is like exploring all the solutions, all in parallel.
Exactly. Like a massive team, each tackling a different part of the problem all at the same time.
That's where the speed comes from.
Exactly. But there's a catch. We don't have direct access to all those calculations happening parallel. Think of a lottery. You have all these tickets, right? Different number combos representing all the possible calculations happening.
Okay.
But when you measure the system, it's like you're only picking one winning ticket, one result.
So all this power, but we only see a glimpse of it in the final output.
Precisely. This is where algorithm design is key. Got to structure the problem so that one measurement gives us meaningful information.
So it's not just raw power then, it's using quantum mechanics strategically.
Exactly. And a prime example. The Deutsch-Jotze algorithm. Imagine a game show.
Oh, I like game shows.
You're presented with a box, mysterious box.
Ooh, what's inside?
It's a function. Black box takes a string of bits as input, spits out a 0 or a 1.
Okay.
Your job, figure out, with as few peaks as possible, if this function is constant, always the same output, or balanced. Produces 0 half the time, 1 the other half.
So, like, is the coin rigged, or is it a fair toss?
Exactly. A classical computer needs to query the box multiple times. Worst case, it might need to try almost every input.
That could take forever.
But a quantum computer, using Deutsch-Jotze, solves it with one query.
One. Half.
Here's where it gets quantum weird. Superposition and phase kickback.
Phase kickback. Okay, now we're talking.
Imagine a light switch. On or off, right, that's the output. 0 for off, 1 for on, phase kickback. It's like flipping that switch subtly without touching it. We manipulate the quantum state of those input qubits.
So we don't change the output, but we're like leaving a mark on the quantum state to tell us about the function itself.
You got it. We encode the information almost like in the shadows. And to read this information, we use a Hadamard gate. It transforms that hidden phase information into something we can measure, something we see in the output.
So it's like a decoder ring, revealing the hidden message.
Exactly. And the whole process, superposition, applying the function, phase manipulation, measuring the output, all within a single query to that black box.
It's amazing how quantum mechanics lets us extract information in ways classical computers can't even fathom.
And this is just the beginning. The Deutsch-Jotze algorithm, it leverages parallelism, a phase kickback. There's a whole world of other algorithms out there.
I'm ready to explore.
Each using different quantum phenomena to tackle specific problems with incredible efficiency. So, ready to dive into Shor's algorithm.
Oh yeah, Shor's algorithm. This is one that can, like, break the internet, right?
Well, not the internet itself, but it could crack the encryption that protects, well, a lot of what we do online. Online banking, e-commerce, that kind of thing.
Whoa, okay, that's still huge. How does it do that?
It comes down to a problem that classical computers they struggle with, factoring really large numbers.
Factoring? You mean like finding the numbers that multiply together to get a bigger number?
Yeah, exactly. Sounds simple, but when those numbers get big, the time it takes for a classical computer to find those factors, it just explodes.
It's like find the factors of 15 is easy, but if you have a number with hundreds of digits, forget about it.
Exactly. And that's what our current encryption relies on. That factoring these giant numbers would take classical computers like millions of years.
But Shor's algorithm, it changes that, right?
It does. It takes a shortcut, a quantum shortcut.
Okay, can we get a glimpse into this shortcut? How does it work?
It transforms the factoring problem into a different problem, something quantum computers excel at, finding the period of a function.
Period, like a wave.
Exactly. Imagine a wave repeating over and over. The period is the length of one complete cycle.
Okay, so how do waves and factoring numbers, how do those two things relate?
There's a mathematical function related to factoring that has a repeating pattern, like a wave. Shor's algorithm uses quantum mechanics to find that period really fast.
I'm trying to picture this. Finding the period of a wave helps you find the factors of a number. Those seem like totally different things.
It does seem like a jump, but there's a connection. Once you know the period, you can use some math tricks, number theory, to get the factors of the original number.
It's like a mathematical detour. That leads you to the treasure, the prime factors.
A very clever detour, and one classical computers just can't take.
So theoretically, with Shor's algorithm, a quantum computer could crack those codes that protect everything online and do it way faster than a regular computer.
In theory, yes. But there's a catch, a big one.
Oh, there's always a catch.
Building a quantum computer that's powerful enough, stable enough to run Shor's algorithm on those massive numbers we use for encryption, well, that's still really hard. We're not talking about factoring 15 here.
So the theory is there, but the tech isn't.
Exactly. We need thousands of qubits, and they need to maintain their quantum states for long enough to do these calculations. And right now, we're still dealing with noise, decoherence.
Noise, like static.
Sort of. In quantum computing, noise is any unwanted interaction. It messes up those delicate qubit states, like trying to balance a spinning plate while someone's shaking the table.
Oh, that sounds impossible.
It's a major hurdle. And then there's decoherence. It's like quantum entropy. The system, it wants to lose its coherence, its entanglement. It wants to go back to being classical.
So it's a race against time. Do the calculations before the qubits lose their quantumness?
Exactly. But despite these challenges, we are seeing progress in quantum hardware. It's remarkable. Just a few years ago, the largest quantum computer had, 72 qubits. Now we're seeing systems with hundreds. It's moving fast.
So a quantum apocalypse, where all our encryption is broken overnight, that's not happening tomorrow. But it is something we need to be ready for.
Absolutely. That's why there's this whole field, post-quantum cryptography. People are working on new encryption that can resist both classical and quantum computers.
It's like a cryptography arms race.
Good analogy. Exciting time to be following both quantum computing and cryptography.
It really is. Okay, so Shor's algorithm, everyone talks about breaking codes. But what about the positive side? What other problems can these quantum algorithms solve?
Great question. Code breaking gets all the headlines, but quantum algorithms could revolutionize lots of fields. Medicine, materials, science, finance, even AI.
Oh, now you've got me interested. Give us some examples.
All right. Medicine. Imagine simulating molecules at an incredible level of detail, down to the individual electrons.
That would be amazing. What kind of impact could that have?
Well, we could design drugs so much better. Target specific proteins and diseases, more effective treatments, fewer side effects. We could even simulate really complex biological processes, understand the root causes of diseases in ways we never could before.
That would change everything. What about materials science?
We could design totally new materials with properties we can only dream of right now, superconductivity at room temperature, materials that are incredibly strong and light.
Wow, lighter, stronger, more efficient. What could we do with that?
Think about aerospace, energy, electronics, planes made of these super strong, ultralight materials, batteries that store way more energy, solar panels that are way more efficient.
I'm seeing a pattern here. These quantum algorithms, they're really good at optimization problems, right? Where you have to find the best solution out of tons of possibilities.
You're right, and that's why they're so promising for finance and AI.
How so? What could they do in those areas?
In finance, maybe optimize investment strategies, manage risk better, even come up with new financial instruments.
Get AI.
They could speed up machine learning, make AI systems much faster, more efficient, maybe even develop totally new AI algorithms, ones that can tackle problems that are just impossible for classical computers.
It's not just about, breaking codes or encryption. It's about finding better solutions to problems, really hard problems.
Right. It's about finding those solutions in fields where we struggle today.
Quantum computers, though, they won't replace our everyday computers, will they?
No, not replace. They'll probably work together. Each has its own strengths.
Like a powerful duo.
Yeah, a partnership. And that's exciting to think about the future, how that'll all play out.
Quantum computing, it's it still feels young, like we're just starting to grasp what these algorithms can really do.
We are. Early days. And there are still those hurdles to overcome.
Like building those quantum computers with more qubits, right? I was reading about this back in 2018. The biggest one only had around 72 qubits.
Yeah, 72. Scaling that up, keeping them stable, coherent, it's a massive challenge. The more you have, the more complex the whole system becomes, harder to control.
Because each qubit is so delicate, so easily disturbed.
Exactly. It's like, imagine trying to conduct an orchestra, but each instrument, the slightest breeze, throws it off key.
And noise must be a big problem, the more qubits you add.
Huge problem. Noise, it's any unwanted interaction, disrupts the quantum state. It's like trying to have a conversation in a really loud room. You know, the more people talking, the harder it is to hear.
So we need to build not just bigger quantum computers, but better ones, right? Ones that can handle that noise.
Yes, less susceptible to noise. And decoherence, too. That's a big focus of research. You know, new types of qubits, more robust. And error correction techniques, that's key.
Error correction, so like having someone checking for typos and fixing them as they happen.
Great analogy. Error correction, that's vital for building fault-tolerant quantum computers, ones that can actually compute reliably, even with some noise.
Sounds like a huge undertaking.
It is, but the progress is impressive, honestly. People are researching different qubit designs, each with pros and cons, and those error correction codes are getting so sophisticated.
So it's a multi-pronged attack.
It is, and it's not just hardware, it's the algorithms, too. People are designing algorithms that are more noise resistant, so even if some qubits go haywire, you still get good results.
Like a ship that can sail through a storm.
Exactly. We want quantum computers that are powerful and reliable, you know, that can weather the quantum storms.
So where do we go from here? What does the future hold for all of this? For quantum computing, these amazing algorithms?
That's the big question, isn't it? It's wide open. What we talk about today, it's just the tip of the iceberg, really.
It feels like we're on the verge of something huge.
We are, but a lot to learn still. It's like, imagine standing on the shore of this vast ocean. We've just dipped our toes in, gotten a taste of what's out there.
Exciting time to be alive to see this unfold.
It is. Who knows what we'll find, what we'll discover.
I, for one, am ready to find out. This deep dive, it's been amazing. Thank you for taking us through all of this.
It's been a pleasure. And as we've seen, these quantum algorithms, they hold the key to so much. A future where we can solve problems that seem impossible today.
A future worth exploring.
Absolutely. So keep learning, keep asking questions, and keep diving deep into this world of quantum computing.
Because the more we learn, the more we realize just how much more there is to learn. Until next time, may your qubits always be in superposition.